Section 9.4 is comparisons of series. In this section, we're going to learn two new tests, the direct comparison test and the limit comparison test, that can be used to determine if a series converges or diverges. Let's start by looking at the direct comparison test. Now, the direct comparison test says, let 0 be less than a sub n, which is less than or equal to b sub n for all n. If the sum from n equal 1 to infinity of b sub n converges, so if this series converges, and if you look here, b sub n is the bigger series, then a sub n must also converge. A sub n here, if you look at it, is your smaller series. So what part A is saying is that if the bigger series converges, the smaller series must also converge. To use the direct comparison test to show that your series converges, you have to find a comparable larger series, show that it's larger than your given series, and then by the direct comparison test, your series must also converge. Part B says, if the sum from n equal 1 to infinity of a sub n diverges, remember a sub n is your smaller series, then b sub n must also diverge. And b sub n, remember, is your bigger series. So what this is saying is that if the smaller series diverges, the bigger series will also diverge. What we're going to do is show that a comparable smaller series diverges, which means that our series will also diverge. So to use the direct comparison test, you look at your given series and decide what to compare it to, something that you know diverges or converges. Usually we're going to look at a p-series or a geometric series and do a comparison. If we think that our series should converge, we need to show that it is smaller than our known series. If we think that our given series will diverge, we need to show that it is larger than our known series. Now please note that the direct comparison test does state that 0 has to be less than a sub n, which is less than or equal to b sub n for all n, but because the first few terms in your series are not going to change whether your series converges or diverges, we can modify that to say 0 less than a sub n less than or equal to b sub n for all n greater than some integer n. What that means is that when we're doing the comparison, if we say this series is larger after n equal 5, then that's okay that it wasn't larger for the first 4 terms. Because again, the first few terms of an infinite series are not going to change whether that series converges or diverges. Let's use the direct comparison test to determine the convergence or divergence of the series. Example 1 is a sum from n equal 1 to infinity of 1 over n squared plus 1. If we're using that direct comparison test, first we need to figure out what to compare it to. We will usually compare it to one of our known series. Well, what are our known series? The ones that we know are p-series, and p-series look like this. The sum from n equal 1 to infinity of 1 over n to the p. We know here that if p is greater than 1, we converge. And if p is less than or equal to 1, we diverge. Our other known series is geometric series. Geometric series look like this. The sum from n equals 0 to infinity of a times r to the n. We know here that if the absolute value of r is greater than or equal to 1, we diverge. And if the absolute value of r is less than 1, we converge. So we look at our given series. This is the given series. And what we need to do is figure out, should I compare this to a p-series or should I compare it to a geometric series because that's what's known? Well, if you look at the given, it looks like a p-series. Why does it look like a p-series? Because it has a variable raised to a power. In order to figure out what to compare it to, I have to do leading term over leading term and reduce if necessary. So what is the leading term of the numerator of the given series? 1. What about the leading term of the denominator of the given series? N squared. Well, I can't reduce that because it's already in lowest form. So what I'm going to do is I'm going to compare this to this series, the sum from n equal 1 to infinity of 1 over n squared. Why am I going to compare it to this? Because I know what it does. It's a p series. Here p is equal to 2, and we know that that means that we are going to converge. Why? Because 2 is greater than 1. So if we converge, if the known converges, what we need to do is show that it is bigger. It must be the bigger series. We need to show that it is the bigger series. Well, the direct comparison says we have to let 0 be less than a sub n, which is less than or equal to b sub n. So the bigger one is b sub n, which means this guy here is my b sub n, and then this guy in this case is going to be my a sub n. My known is going to be my a sub n. Why? Because we have to show this guy's bigger, which means it must be b sub n. Let's place our a sub n and b sub n in this inequality and then try to show that it is true. A sub n is my given. That's your 1 over n squared plus 1. Is that actually less than or equal to my known, which is my 1 over n squared? Well, let's cross multiply to see if this is true. 1 times n squared is n squared. Is that less than or equal to 1 times n squared plus 1 is n squared plus 1. Is n squared less than or equal to n squared plus 1? Yes, that is always true. Therefore, by the direct comparison test, and I'm abbreviating DCT for the direct comparison test, our series converges. To recap, what you do is look at your given and figure out, do you look like a p-series or do you look geometric? Once you figure out which one you look like, you find leading term over leading term, reduce, and that's how you determine what to compare it to. When you figure out what to compare it to, you have to figure out, what does this known series do? Does it diverge or converge? If it converges, it's got to be the bigger series. If it diverges, it's going to have to be the smaller series. So figuring out if it converges or diverges allows you to figure out, is it supposed to be the b sub n, the bigger one, or the a sub n, the smaller one? Once you determine which one of the series is b sub n and which one is a sub n, then you put it into your inequality and then determine whether your inequality statement is true or not. If it holds true, if this is true, then you can say that by the direct comparison test, your series either converges or diverges depending on what you have. Now notice, we did this exact same series in section 9.3 using the integral test, and using the integral test, we determined that the series converges. So just to let you know, there is more than one test that can be used to determine if a series converges or diverges. Let's keep going. Number 2. Again, we're supposed to use the direct comparison test to determine the convergence or divergence of the series. The first thing we do is figure out, do I look like a p-series or do I look like a geometric series? Well, I look like a p-series. Why? Because it's a variable raised to a power. Which p-series should I compare it to? We'll look at those leading terms. Leading term in the numerator is n. Leading term in the denominator is n to the fourth. If I were to reduce that, that's a 1 over n cubed. That means I'm going to compare it to the p-series, the sum from n equal 1 to infinity of 1 over n cubed. Well, here p is equal to 3. 3 is a number that's greater than 1, therefore I know that we will converge. Since that series converges, remember, it has to be the bigger series. Since it has to be bigger, it is your b sub n, and your given is your a sub n. Then we go to our inequality, 0 less than a sub n less than or equal to b sub n. A sub n is our given, n minus 2 over n to the fourth plus 1. is that actually less than or equal to b sub n, which is 1 over n cubed. Cross multiply. N to the fourth minus 2n cubed, is that less than or equal to? Cross multiply. N to the fourth plus 1. If you can't tell at this moment if this inequality is true, you can use algebra to simplify it. You can cancel out the n to the fourth from both sides, and all you're left with at this point is negative 2n cubed less than or equal to 1. Is that a true statement? Yes, a negative is always going to be smaller than 1. Therefore, by the direct comparison test, your series converges.